What if there are 4 groups of electrons sticking out of the atom? That means a steric number of 4. Here are some of the several ways that that could happen. You can have 4 single bonds sticking out of an atom, or you can have 3 single bonds and a lone pair, or you can have two single bonds and 2 lone pairs, or you can have a single bond and 3 lone pairs. Okay? So when you have 4 groups sticking out of an atom, those 4 groups will tend to be oriented towards the corner of what's called a tetrahedron. So it looks like this. So this one, you have methane, for example, has 1, 2, 3, 4 groups. They don't actually lie. These 4 groups are not actually on a plane, because this would be 90 degrees right here. Actually, in reality, that's not going to be 90, because the molecule is capable of achieving an angle that's bigger than 90 degrees. Okay, and this is what it looks like. You have to think in 3 dimensions. Okay, so here's your carbon right here. Here's your 4 oxygens. 1, 2, 3, 4. Okay, imagine. Okay, connecting these 4. Okay, a tetrahedron. Okay, is a pyramid, basically a pyramid with a triangular base. So here's the base of that pyramid right there. Okay, and you have another triangle over here, and then you have another triangle over here. You have another triangle back there. Okay, and a triangle over here. So 3 triangles up there, and then you have a triangle at the base. So 4 triangles forming a perfect pyramid. So tetra means 4, hedron means side, so it's a 4-sided solid, and which is basically a pyramid. So the carbon atom, the central atom, is at the center of the pyramid. Now, any angle that goes to that center of that pyramid, okay, from the corners of the pyramid, can be shown by geometry to be 109.5 degrees. You just use Pythagorean theorem to do that, because you can show that these, in fact, would be the diagonals of a cube, and that would be the other diagonal of a cube down there. But if you can't visualize it, it's okay. The important thing to realize is that any angle that goes through the center of the pyramid from the corners of the pyramid would be 109.5 degrees. Okay, so methane, we say, has a tetrahedral center. So carbon here is a tetrahedral center. Tetrahedral center. And the shape of the molecule itself is also called tetrahedron. So the shape is tetrahedral. Okay? Now, you can think of this thing right here that we're drawing as a projection. Okay? This is like, imagine these 2 are actually sticking out towards you. These 2 CH bonds sticking out towards you, and these 2 CH bonds back here are sticking away from you. Okay, so they're forming a 109.5 degree angle with respect to each other. And so what you're seeing there is basically a projection on the plane. Okay? Now, what if one of those 4 groups doesn't have an atom on the other side? So you have a situation, so methane is like this. You can have a situation where you have 3 of the groups are single bonds, and the 4th one is a lone pair. So methane, you would say, is type AX4. Okay, central atom A with 4 atoms attached to it. Ammonia is an example of a tetrahedral center. Again, steric number is still 4, with a lone pair. Okay, so here's the Lewis structure for ammonia. You have 3 single bonds and a lone pair. Okay, so those 3 single bonds are right there. This is the nitrogen, and you have your 3 hydrogens there. So the 3 hydrogens form the base of a pyramid. It's not quite as perfect as the pyramid in methane, because there is no atom up here. So there's no atom there. So your pyramid is sort of flattened out. So even though the nitrogen atom here is still called a tetrahedral center, the nitrogen atom is a tetrahedral center, so you say the electron domain geometry around nitrogen is tetrahedral. You can say the groups of electrons are sticking out towards the corners of a tetrahedron. The nitrogen atom is a tetrahedral center, but the molecule itself, we don't call it tetrahedral, just to make a distinction between that, between this structure and the perfect tetrahedron that we saw for methane. So we call this trigonal pyramidal. So it still has a triangular base and it still looks like a pyramid. Okay? The nitrogen, by the way, in this particular case, is bonded to only 3 atoms. So we say it has a coordination number of 3. Okay? So 3 of those electron domains terminate on an atom. Okay? The 4th electron domain is a lone pair. So this molecule we say is type A. The geometry of this molecule, ammonia, is we say AX3E. So the 3 means there are 3 atoms attached to the central atom. So the X's would be, in this case, the hydrogen. The A would be the nitrogen. And the E here stands for the lone pair. So you have 1 lone pair and 3 single bonds sticking out of your central atom. Now, the H&H angle, as you can see here, is given as experimentally, that's 107. By the way, that's an average, okay? Because all these atoms are always moving up all the time. So that's the average H&H angle. So if I were to ask you on a test, what is this angle? Even though it looks like 90-degree angle, it looks like a right angle there. The answer I'm expecting from you on the test would be what that angle would be in the real three-dimensional representation of the molecule. And the answer would be 109.5. Well, the perfect answer here is 107, but I'll take 109 because that's a tetrahedral angle. Okay, so 109.5. But actually, in reality, that's 107 because this is distorted. Okay? And the reason for the distortion is because this lone pair right here is bulkier than the single bond, so it pushes those single bonds away, farther away from it, so they're a little closer together, so the H&H angle is less than 109, it's 107. Okay, so ammonia has a tetrahedral center, but its shape is trigonal pyramidal. Let's take a look at the situation where you have a tetrahedral center with 2 of those electron domains being lone pairs. That's what happens when you have water. So water, okay, here's a Lewis structure for water, has 1, 2, 3, 4 groups sticking out of it. So steric number of oxygen in the water is 4. Okay, but if you look at your tetrahedral structure, you have 2 of those groups don't have an atom on the other side. Those are just lone pairs. So when you're describing the shape, we say the water molecule is a bent molecule. Anytime you only have 3 atoms, there's only 3 ways to describe it. Either the atoms are in a straight line, in which case it is linear, but in this case, the molecule, the shape of the water molecule is bent. The center, the oxygen center, is a tetrahedral center. Okay, you'll notice this oxygen has 2 atoms attached to it, so its coordination number of 2, and the number of lone pairs is 2. So this molecule, we say, is type AX2E2. Now look at the angle here, 104.5. That's even smaller than for ammonia. So remember the perfect tetrahedral angle is 109.5. For ammonia with 1 lone pair, you have 107 degrees. This is 104.5 degrees. This is even smaller because you now have 2 bulky groups there, 2 lone pairs on the central atom, which will push those single bonds closer together.